Good afternoon, everyone, and thank you all for joining online. Today we have Dr. Elizabeth Barnes, who's coming to us virtually from Colorado. So Dr. Barnes completed her PhD at the University of Washington, working with Professor Dennis Hartman in 2012, and then joined Colorado State University in 2013 as an assistant professor of atmospheric science. Her interests include Earth system predictability, jet stream dynamics, Arctic mid-latitude connections, seasonal to decadal climate prediction, and especially more recently, data science methods for Earth system research, including machine learning and causal discovery. So today she'll be talking to us about using explainable AI techniques to understand climate change. And with that, I will hand it over to Dr. Barnes.
Thank you, Costa, and thank you, everybody. It sounds like you have a lot of in-person talks in your future, so thank you for doing yet another virtual seminar so that I could participate. So this evening, I'm going to tell you about the work we've been doing thinking about using AI or machine learning to view anthropogenic change. That includes climate change, but as I'll show you, I'm going to give you a few examples of also changes in the land surface due to human activity. For those of you who don't know me, my background really is in climate science and climate dynamics, specifically large-scale atmospheric dynamics. So in the last 5 years or so, I've gotten much more interested in the data science tools we use to do climate science. And so that's the perspective I'm going to give today. First of all, I always want to make the really important point that this is very much a group effort. I sort of see myself some days as a spokesperson for all of the cool work that's being done in my group. And so you'll see heads popping up when I'm showing different graduate student and postdocs work, and just know that this is really coming from a lot of discussions with these wonderful people, especially on Zoom, unfortunately. Okay, so the toolbox. As geoscientists, we have a big toolbox. We have theory. That's a pretty important tool. Spectral analysis, correlation, EOF or principal component analysis. We have our dynamical models. I think one of the most important tools that require all these other tools to be created and used. And then, even at its simplest, we have linear trend detection. Thinking about just climate change, are the temperatures going up, and fitting a line through it. So I really see machine learning, and I know many of you here also think about machine learning, but I see it as one particular tool in this much larger toolbox that we have. And I want to tell you today how we're using this tool to study climate science and climate science questions. All right. So one of our jobs, at least in my opinion, as scientists, is to sift through piles of data and try to extract useful relationships that apply elsewhere. They're applicable out of sample. You could call this in some ways learning physics. The hope is if it works somewhere in one place, the physical laws still apply elsewhere. And I would argue this is what many machine learning methods are designed to do, not discover physics themselves, so I'll be careful there, but to help us sift through piles of data and find relationships. So there's been a lot of work done in machine learning for climate science in the past decades. I will point out that really does go back decades. However, in the past 2 to 3 years, there's been a lot of a sort of an explosion of this work. One of my favorite applications still came out in 2020, and it's a colleague saw this example from NVIDIA of the commercial application of someone coming in and erasing part of an image and training an AI or machine learning algorithm to try and fill in that image again. And you can see that it filled in the eye, so it knew there was an eye, but if you look really carefully, it's certainly not perfect. There's makeup. The makeup isn't symmetric across the model's face, etc. So this colleague saw this and said, hey, this seems a lot like temperature reconstructions over the past few hundred years. So can I use this pre-trained model and actually retrain parts of the weights to infill data of, in this case, going back to the 1800s. And in their paper, I think it's just a great paper. They do a lot of checks and balances, but they show that this temperature reconstruction here on the right, which provides evidence of a very strong 1877 El Nino, which it turns out has been recorded by hand by people that live in South America writing about it, but some reconstruction methods actually don't capture this. So that was an argument that maybe this particular method is providing something new on top of the reconstruction methods we already have. I just think this is really fun. I'll tell you, one of the things I'm having the most fun with is finding ways to take these awesome tools that are being developed in other fields and bring them over to our fields. So this is one of the reasons I find this example so much fun. There are many other examples as well. Here is just sort of a long list of them. Detecting, so extreme. Wow, extreme detection. So there we go, extreme event detection. Instead of dogs and cats, you can look for different features in, say, the water vapor field. Equation discovery, this is becoming more used now. Can we input actual, I guess, variables or combinations of variables such that the machine learning algorithm can help us discover equations themselves? This is so cool. Weather prediction, just general here. And then, of course, convective parameterizations or parameterizations in general in models. Can machine learning either replace parameterizations or at least help us develop better ones? And then finally, just a little bit, maybe a little bit a step away from the science itself, but climate change communication. You'll see machine learning being more and more used to actually help people visualize the world that we're entering or that we're already in this case, using GANs to show what your street might look like with flooding or inundation due to sea level rise. So there are lots of ways that machine learning is being used for climate science already. And I sort of put them into a few categories. So I put them into these three. So why would we use it for science? One is just to do it better. Maybe convective parameterizations and models aren't perfect and we can use machine learning to help make them better or more accurate. Maybe you already know how to do it, but you want to do it faster and cheaper. So for example, radiation code in models can be quite slow. So maybe we can just use these methods to speed it up. And then finally, to learn something new. So I always say, even if it's worse and it's slower, we can still learn science from these methods, that is from the data. And so I think this last one is very relevant for research, although they're all relevant, but this last one's very relevant for research, and that I will touch on that at the end here. So specifically, I'm going to go through three main examples. The first is really about just doing it faster or cheaper. And then number 2 and 3 are taking the approach of how can we learn something new about the climate system or about climate change. All right, so here's the big question here, or the big driver of this talk. Humans are changing the Earth in profound ways, and the question is, how does this differ around the planet, and how has it changed over time? This is very general, and so what I want to talk to you about, of course, is some of the ways we're using machine learning to do this. So an example one really is looking at the human footprint, or how humans have changed the land surface. And this is work that we did last year. And I will note that by the we, the first author here is Patrick Hughes, who's also my husband. We were stuck in a house together attempting to raise 2 children during COVID, and we would sort of pass the torch, if you will, while we were working on this project together, which was a lot of fun, actually. So there are lots of human pressures on the landscape, and there are metrics out there to quantify these already. And it's really important to map these efforts because some changes may be reversible, and there are certainly these metrics are being used to track how different countries and regions are changing in terms of things like sustainability issues and deforestation, etc. One of the problems, though, is if you can imagine figuring out what humans are doing to every square foot of land on the globe is an incredibly challenging task. And current efforts tend to lag the present day by 5 or more years. So that is, it takes so much effort to put together these metrics, but by the time that they're all done, it's been about 5 years since that data was up to date. So there are many metrics out there already for this, I will point out. One of well-known method is by Williams et al., and they created the Human Footprint Index. And this is a map of that Human Footprint Index for the year 2000. The yellowish regions are higher values, closer to 1, implying, if you will, it's a shopping mall with a parking lot. And the dark blue or purple, really dark colors, those imply, humans really aren't changing the landscape there. So this, you can look at your favorite location. It's an awesome picture that you can just stare at for a while. But our question was, can we do this faster or cheaper using machine learning methods? Because the current method is to have humans and computers take all of this information about built environments, population density, croplands, pastures, etc. They have to go and collect all this information in order to put it into a single index. So what we did is we thought, can we take Landsat imagery alone? And in this case, we're just taking 3 different bands of these small snapshots of Landsat imagery, input it into a CNN, so a convolutional neural network, a type of machine learning model, and have it predict some value between 0 or 1 of how much the humans have been impacting that land surface. That is, can we have it predict this already created human footprint index? So in this way, we already have, if you will, the label. We didn't have to go and figure it out ourselves. You know, this group has been working for years to create this index. So we did this all over the globe for all regions using Landsat imagery. It turned out for me, since I was one of the lead in terms of analysis here, my understanding of software engineering is very poor, and this for me was big data. So I will talk a little bit about that later. So the whole idea here is we'll train on the year 2000 when we have this human footprint index already created. But then, because Landsat imagery is coming out every year, we can actually use that then to create an up-to-date human footprint index for the year 2020. And one of the nice things as well is Landsat imagery has clouds, but there is a the data exists out there if you will, clean to actually be cloud free for every year, in which case we didn't have to do that work either. So the idea here is to make a prediction between 0 and 1 of this human footprint index. So here's our machine learning, our ML-HFI as we call it, for the year 2000, and the originals in the bottom left, and of course you can't possibly compare them right now by looking, but the point is we did a lot of metrics and analysis to convince ourselves it's actually doing a pretty good job of taking Landsat imagery and from that predicting this human footprint index. So the whole idea here is this is for the year 2000 when we already had a human footprint index, but now we can use it to estimate, in this case, the human footprint index for 2019, because we have Landsat imagery and we can just run it through our algorithm and actually make a prediction. All right, so if I flip back and forth a little bit, you might be able to see certain regions turn yellower. And that is, again, the human footprint index increasing or humans impact increasing. So, and I'll show you that a little zoomed in a minute. But a big question that comes up, are these predictions any good? How can we check we have the right answers for the right reasons here? I will tell you, first of all, we did quality control over 2,000 regions of the globe, actually looking at Google Earth and using their time lapse and making sure the changes made sense. But on top of that, you can't do that for every location on the globe. So how else might we be able to do that? And so if you've heard the phrase opening the black box, here are 3 examples of papers about opening that black box or trying to explain what your complex deep machine learning algorithms are doing. And these are 3 examples of papers for geoscience applications. So there are more coming out, honestly, every few months, but these are some that I think go into the detail for our field. One of those methods that I have been using in my group, although there are many others that do somewhat similar things, is Layerwise relevance propagation. And it's an attribution method. And here's why I like it. It sort of allows me to think like I was already thinking about climate science and climate science applications. So what it does is, after you've trained your neural network and you want to understand, I've trained a neural network to predict if there's a cat in the image, and you push an image through the network and it says the probability there is a cat in this image is 0.8. So great. But as a scientist, you might say, well, I want to understand why it thought there was a cat in this image. Where did this 0.8 come from? So what these attribution methods do, or specifically Layerwise relevance propagation, is it takes that 0.8 and it propagates it back through the network, distributing that 0.8, what they call relevance, all the way back until you create a heat map that can be interpreted as the amount that those pixels are relevant or contribute to that final 0.8 prediction. So in this case, rather boringly, it tells us that the network knew or thought there was a cat in the image because it looked at where the cat was. So this is pretty boring and obvious, but it gets a little more interesting as you for some applications that I'll show you in a minute. All right, so why might I want to use these this layerwise relevance propagation method, or XAI? Well, one reason is to help identify problematic strategies in the learning of the network. So we want to, as I said, ensure the right answers for the right reasons. If you've ever seen me give a talk, I apologize. You've seen this example many times then, but it's one of my favorites. So here are some images with horses, and a neural network was trained to identify if there were horses in the image. So hopefully you agree, there are horses, great. So the network also thought there were horses in these images, and the question is now, why is that? So you can go and make these heat maps, and the red regions here are the regions that LRP said are most relevant for knowing there was a horse in the image. And if you sort of squint, you can convince yourself that they overlap with horses. So, okay, the network was looking where there were horses to predict that there were horses. This is a lot like the cat example. But how about the next example? Okay, so 3 more horses in 3 more images, and the network also said, yes, there are horses in these images, and you can go and use these attribution methods to tell you where it looked. And instead of looking where there are horses, you'll notice that the brightest colors, the most relevant regions of this image, were actually in the bottom left-hand corner. And that's where the copyright symbol was. So that is, the network is, if you will, learning the right answer for the wrong reason. It has learned to identify these copyright symbols as being representative or indicative of there being a horse in the image, and it hasn't really learned about horses at all. This is a problem because if I go and take a picture of a horse and I put it into this network, it will likely say there is no horse because I don't have the right copyright symbol. So this is the idea of how you can use XAI to identify problematic strategies and ensure that you're getting the right answers for the right reasons, or not ensure, see whether you are or not. Of course, once you discover you're getting the right answers for the wrong reasons, you now have to go about figuring out how to fix it. So returning now to this machine learning human footprint index, we use this method of LRP to understand how the network, or try to understand how the network is making its decision about changes in the human footprint index. So here are 6 example regions across the globe. In each case, the leftmost image is the year 2000 image. The middle image is the year 2019 for 2019. And the rightmost image is the relevant regions for that 2019 prediction. So in all of these cases, the human footprint index went up over those 20 years. And you can start to see that indeed the network appears to be looking at or identifying human-made changes. For example, wind farms going in, a wind farm installation in Texas, a bridge and buildings going in, urbanization there in China. And actually a really interesting one is artisanal mining in the bottom right-hand corner in Indonesia. Interestingly, this was an example where the original human footprint index did not say humans were active. And it turns out this was a unreported mine, artisanal mine. And we actually were able to go in and to figure out what it was, we actually had to go and use Google Translate to translate some local newspapers to figure out what it was. So this is one scenario where the machine learning method actually allowed us to do it a little bit better by identifying this mine that was otherwise not identified. I will say there are lots of places where it also got it wrong, and I'm happy to talk about that too. So once again, these are those layer-wise relevance propagation heat maps to help us ensure that we're getting the right answers here for the right reasons. So why might you care about explainable AI if you're interested in machine learning for geoscientific research? I already mentioned identifying problematic strategies. Another is just generally building trust, which I think go hand in hand, but are not exactly the same. So helping you evaluate trust in your network. Another is choosing the approach. So one thing I didn't mention is there are many Landsat channels one could use, and we actually use explainable AI to help us identify which channels were most important to a network's correct prediction, so we could remove the channels that weren't really being used and save on memory. And finally, number 4 here is to learn something new. So again, we can use these explainable AI methods to learn something new about the system we're interested in. So in this case, you can think about data going into your machine learning network, outputting a prediction, and you may or may not care about that output prediction, but what you really care about is what did the network learn in the data? How was it able to make a correct prediction in the first place? And that's where we're using XAI quite a bit in my group. So for example, number 2, that will take that to using XAI to identify indicator patterns of force change. So when we think about force change here, I mean specifically anthropogenic climate change. There are a lot of things that come into this question of detecting force change. One is, what are the patterns of change? Which geophysical variables are interesting or changing the most? Another is the timing of detection. When can we detect patterns of force change amidst natural variability and climate noise? And finally, model evaluation. Do climate models simulate these changes correctly? Or put another way, even, do they simulate these changes in similar ways or in different ways from each other? So also just model comparisons. So one of the ways we have approached this is doing something a little odd, which is we have taken a lot of climate model output and we take yearly maps, in this case of surface temperature. So every year has its own map. And what we've done is we've trained a neural network to ingest that single map and predict the year from which that map came. So what year is that map from? Now this is, I can go into details later during questions if you're curious. But first of all, it seems like a sort of silly problem because nobody would ever care for me to tell them what year it is on its own. Everybody knows they can look at their calendar, they can look at their phone, right? But the idea here is not so much predicting the year. The idea is if the network is able to do this task, then it has to learn regional signals that are reliable indicators of that year. And the only way to do that is find indicator patterns of force change amidst the noise, something that distinguishes, say, 1930 from 2030. And that's going to be this response to anthropogenic forcing. So we did this, and I can show you on the x-axis here are some results, is the actual year of the map that we gave the neural network. And on the y-axis is the predicted year. So the one-to-one line here would be a perfect prediction. All the colored dots are different climate models, and the colors actually denote climate models that weren't used for training, so that they were unseen, if you will, by the network. So this is for surface temperature maps from CMIP5 climate models. And the big point here is a lot of the dots, especially after about the 1990s or so, start to lie along that one-to-one line, suggesting that the neural network has learned patterns in the data that tell it what year it is. On top of that, the white dots here are actual observations that the network wasn't trained on at all. But after we have a trained network to predict a year from a map, we can input temperature maps from any data source. In this case, we chose to use surface temperature observations. And in this case, the fact that the white dots also lie along the one-to-one line, that is, the network is able to identify what year it is from observed surface temperature maps, suggests that what the network learned from climate models is, at least in part, applicable to the real world. That is, it's learning something that we actually are seeing. All right. I already said this, but I think predicting the year seems pretty silly. But the whole idea here is not the prediction itself, but what if we could learn which regions of the globe or which variables were most relevant to predicting the year? That's where we use these explainable AI techniques. So after we make a prediction, we input a certain map and we output a year, we can then use Layerwise relevance propagation to go back through the network and ask which regions are relevant for that correct prediction. Or that incorrect prediction, actually. You can also use this to explore why the network got it wrong. In this case, we're exploring why it got it right. So an example of such a heat map is shown here on the left. So this is that heat map for the year 2015. So where did the network look to determine that the year was 2015? And we can see some well-known regions for climate change popping out. We see, say, the North Atlantic, for example, the Southern Ocean, and we also see Southeast Asia, which we think may be signal from aerosol forcing. Now, we can do this for more than just the year 2015. We can do this for lots of different years. So here are a few different years. We can ask, where did the network look? And I do like to point out at this point that these are indicators of a changing climate. And they're a combination of the climate change amplitude, the response. So this is not just, it's hot everywhere. We know what that looks like. I already showed you that plot. This is, where is the amplitude of the change large, the internal noise or variability small, or at least that ratio is signal to noise is big. Where do the climate models generally agree? And then a geospatial combination of all of these. So that's why looking at these plots is not the same as just looking at the IPCC temperature response. These are different types of plots. So again, we see that the network is looking in different regions to identify different years, suggesting there are different, reliable temperature indicators over these different regions. And I will also point out we've done this for other variables as well, not just temperature. I already mentioned that we think this might be an aerosol signal over Southeast Asia. So the network has learned to identify the response to aerosol forcing in this region and that it's indicative of around the turn of the century. Now, another thing you might notice if you're familiar with temperature change, with climate change, is that the Arctic here doesn't really appear to be popping out. And we know Arctic amplification, or the warming of the poles, is actually amplified compared to the rest of the globe. That's a fingerprint of climate change. So why hasn't the network looked in the Arctic? And the reason is, again, this is not just the change in temperature. This is a combination of that change as well as internal variability and model agreement. And it turns out the Arctic is a region that, while the signal, the temperature change, is large, the internal variability is also large, and models tend to disagree on the timing of, say, sea ice loss. Because of this, the network has learned that this is not a terribly reliable region across the CMIP climate models, and so it looks elsewhere to determine what year it is. So that was all with the climate model results, but what about observations? We can train the network on climate models, but as I said, once it's trained, we can input observed temperature maps and ask it to predict the year. So on the top is the observed temperature anomalies for the year 1997, and we see a very strong El Nino. And indeed, actually, in this case, the network did predict 1997, and we can ask, where did the network look to know that it was 1997? And what we see actually is that the network tends to focus on the Southern Ocean the most in making its prediction. So again, it suggests that it's not just looking at the largest anomalies, it's looking at this combination of multiple things going on at once. And finally, we can get some insights about climate model biases by using another method called backward optimization. I won't go into details here, but it allows us to ask the question, how should we modify the observed 1985 map to get a perfect prediction with our trained neural network? That is, in this case, what we're doing here is we've made the problem harder for the network. We said, you don't get to use the global temperatures. We're going to remove the global mean. That is, every year, the global mean temperature in any one map is 0. So the network can't just, if you will, sort of cheat and just say, well, it's hotter everywhere, so it must be a later year. Instead, it has to look for regional patterns in order to know what year it is. And to do when we ask it to do this, we see that actually it's 30 years off in this case. So the observed map is for 1985, but the neural network predicts it's 2016. So it's wrong. And the question now is, well, how could we have modified this map to make the network actually think it was 1985? And when we do that, we produce a map like the one at the bottom, which suggests these are the regions that we would need to change to get a correct prediction. So what it tells us is actually something about the biases in the climate models on which this neural network was trained. It tells us that the models are too cold over land compared to the ocean in these reliable regions. And it also suggests that models are too warm over the North Atlantic, or this warming hole, if you will. So these are some sort of games we can play with these different methods. Now, this was some of our earlier work, but you might say, well, why are you using temperature or just precipitation? I didn't show you those results, but that's what we've done. What about combinations of these variables? So Jamin Rader, a master's student in my group, started asking, can we combine variables and seasonal informations to perform the same task? And do we get anything for that effort? That is, you could imagine that including seasonal information about precipitation changes or the precipitation pattern could actually allow you to identify climate change earlier. So indeed, that's what he's doing here. He's inputting different seasonal maps of temperature and different seasonal maps of precipitation, all from the same year, and asking the network to predict what year it is. And when he does this, there's, I won't go into all the details here, but again, it's the true year on the x-axis and the predicted year on the y. What we see is that when you combine these variables and seasons together, the network is able to actually identify change slightly earlier than it is with any one of these alone. All right. So in the end, we find actually that the earliest time of emergence of this force change is for seasonal and combined variables, so temperature and precipitation together. And one could imagine doing this now for many different variables, not just temperature and precipitation. Now, what about the explainable AI part? Where is the network looking in these different maps? And this is actually a slightly different question, because when we put in temperature and precipitation together, the network's going to, I would assume, use temperature because that's has such a strong climate change signal. But the idea that precip is somehow adding additional information beyond what we already got from temperature, well, I would like to know where that is. What regions of the globe is precipitation providing a unique signal that we didn't already have from temperature? So Jamin was able to make a relevance map for, in this case, this is June, July, August precipitation, and show that this is the indicator pattern that shows where precipitation provides unique information beyond that of temperature alone. And we see regions like the middle of Africa, and again, the Southeast Asia region over India. So it's popping out. And I will point out that you might say, well, is this just the signal to noise map? And indeed, there's similarities, but they are not the same. So it really shows that the network is highlighting specific regions of the globe to make its prediction. All right, so that's how we're using XAI to think about detecting force change and learning something new about the indicator patterns and these signal to noise, if you will, ratios, but as a combination of signal, noise, climate model agreement, and the geospatial patterns of these signals. So example number 3 sort of takes a step back from climate change and just talks about detecting mechanisms driving global temperatures alone. So that includes internal variability as well as I already mentioned, a forced response. So this is some new work by my postdoc, Zach Labe. I'll mention him in just a minute. But we know that temperatures are going up. We've just been talking about that, detecting this forced response to anthropogenic climate change. But even though they've been going up for decades, we know what this is. Sometimes it goes up fast. The global temperature goes up faster than other times. So for example, we see here a sort of what we are calling a warming slowdown, sometimes known as a hiatus, when that trend line for a decade or so was not as steep as it was previously or afterwards. So one question that Zach has been asking is, can we predict slowdowns in global temperature trends either before they occur or right when they're beginning, right when these slowdowns are starting up? So what he's done here is he's inputting ocean heat content into a really simple neural network and asking it to predict, will there be a slowdown in decadal warming over the next 10 years or not? And if so, he can then use, like, if that's the beginning, if you will, of this warming slowdown, we can then use Layerwise relevance propagation to ask, how did the network know that the temperatures trends were about to undergo a slowdown here? So he's done this and it works. And so the question is, again, using XAI, where did it look? And what we find here, so the top plot is this Layerwise relevance propagation heat map, again, for these correct slowdown predictions. So the network predicting that there will be a slowdown in the next 10 years. And on the bottom is a composite of again, this LRP in yellow, and then also a composite of the upper ocean heat content in colors. And what we find is the neural network is learning off equatorial patterns of anomalous ocean heat content that generally resemble transitions in the phase of what's known as the interdecadal Pacific Oscillation, or a low frequency climate mode that we know is one way to drive global temperature slowdowns, because it actually can provide just a general cooling to the global mean temperature. So this jives with theory and our understanding of possible reasons that we might detect a slowdown. And so this shows, and I should point out actually that while the training was done in a long control run of a climate model, once he's trained the model, he then applies it to observations and is also able to predict the slowdown that we saw just in the last decade. So this also appears to apply to observations as well. So These transitions in these low frequency climate modes can be important for understanding global mean temperatures. And specifically here, Zach found that it's the transitions in the phase of this low frequency mode that gives the network a heads up that a slowdown in the global temperatures may be coming. So Emily Gordon in my group then is asking, can we predict slowed or transitions of these low frequency climate modes? You know, regardless of what's going on with anthropogenic warming and the anthropogenic signal, can we predict when these internal modes of variability might flip sign and change, thus either driving even more warming than we typically see, than we might expect, or a slowdown? So what she's done is she's trained a neural network to predict these transitions in the Pacific Decadal Oscillation, which the canonical pattern is shown here. So what she does is she inputs ocean heat content maps at various levels of the ocean, or I think actually in this case, over different times in the past, and asks in the next 30 months, will there be a transition in this low frequency climate mode? So yes or no. And yes, so the idea here is, you know, if we're sitting here at this orange dot right here, we input some of the past maps to give it temporal information and ask, will the PDO index cross the 0 line in the next 30 months? Will there be a transition? Once she does that, and is successfully able to train the network, once again, we can use explainable AI now, though, to answer the question, how did the network know there would be a transition? What patterns in these ocean heat content maps allowed it to predict a correct transition of the Pacific Decadal Oscillation? And these transition precursors, you can suss out for every prediction made and actually start to try and identify physical mechanisms leading to predictability of these transitions. So on the left-hand side shows the heat map, or the Layerwise relevance propagation heat map, for the most relevant regions for the network to predict a positive to negative transition. And what we end up seeing is that this region, outlined here in pink, is very consistent with already known dynamics of PDO transitions. And so really sort of tells us that we think the network's actually learning the right answer for the right reason based on a lot of previous work. However, going from negative to positive, the network really doesn't focus on the same region and actually puts a lot of emphasis and relevance in the North Atlantic. So that is, the network is looking at the Atlantic Ocean and this interbasin teleconnection, we think, that drives El Nino, which in turn drives the transition. So in this way, we see that the network is actually able to recognize distinct transition mechanisms depending on the state of the system, which I think is one of the benefits of using, say, neural networks rather than just standard linear practice, because it actually allows us to treat these different states in different ways and have different predictability. All right, so wrapping up here, I just want to point out that these are just a few examples of how we're using explainable AI methods in my department. And so here are a few more heads for you, but we're using it to do quite a bit of work on subseasonal to decadal predictability, thinking about the force response and mid-latitude dynamics, and actually seeing if we can use it to develop Green's functions for the circulation. I already mentioned indicator patterns of force change. This involves both in climate change simulations, as well as thinking about climate intervention scenarios. And then finally, I have not talked about this here, but another part of our work is actually thinking about how the tools themselves. Many machine learning tools were not made specifically for geoscience applications. And so one question is, can we take these tools and I guess massage them a bit to make them more applicable to the types of questions that we want answered? And so that includes, how do we benchmark which explainable AI methods are the best for the types of questions we ask? And figuring out how we can create more robust predictions when our data is not infinite and often contains quite a bit of noise. So wrapping up, I always like to end with just a few thoughts of things I'm excited about. One here is knowledge-guided machine learning, or trying to fuse physics and machine learning together to actually make better predictions and better models. A big complaint about machine learning is that it's a black box and we've forgotten about F equals MA. And there are now many people in the field thinking about how to include physical constraints and physics in general in the machine learning framework. Another topic that I'm excited about is transfer learning. So we know our climate models aren't perfect, but we have a lot of data from them. And we know observations, well, they're not perfect either, but they're a better representation, I think, of the real world, but we don't have a lot of those. And so transfer learning is one method in the machine learning community to try and train a machine learning model with imperfect climate model simulations and then update it with observations to attempt to get the best of both worlds. And this has been successfully applied already a few times to climate applications. And this is something I'm really excited and interested in pursuing. And finally, this is definitely not news to many of you. I know there's a lot of people working on CLIMA, but the idea that we can use machine learning methods or data-driven methods to help us improve climate model projections. That may be through improving the climate models themselves, but also helping us with model comparison and evaluation, or bias correcting when we actually know that there are issues and we have yet to solve in our climate models. So I really see these tools as working together rather than separately. So closing thoughts here. I think machine learning is exciting. It's another tool in our toolbox, of which we already have many. And the idea here is that machine learning is not just some black box where it's agnostic to the science and no science can come of it. We can do more than just make a prediction. We can ask the question why. And I've said this for a while now. I think it's a game changer, and the phrase game changer is used so much. But if I could only use it once, I really think it would be here. I do think that the explainability side of machine learning is really a game changer for scientific research. Okay, thank you.